Am I audible? Yeah, okay. So we'll start the class in a second. Just just give me a minute and then we'll start the class. So today we'll be discussing a summary for week 5. And the first thing in week 5 is we'll start with one-one functions. What a one-one function is. So the definition of one function is, let's say you have a function f, then it's said to be a one-one function if at
Ma'am, your
two
voice
points
is
its
breaking.
image is same. Let's say there are 2 points in the domain where your x1 and x2 are in the domain of f.
Can you hear me, ma'am? Your voice is breaking.
So, okay, is it better now?
No, ma'am. No,
No,
ma'am.
Is it
ma'am.
fine?
No, ma'am.
Still not clear, ma'am.
Yes, I can hear you. So I hope I'm clearly audible to you all now, and my voice is not breaking. Is it still breaking? Is,
No, ma'am.
No, ma'am.
okay.
Very clear.
So okay. So we'll start with the definition of one-one functions. It says that if you have to, let's say this is your domain. So by now all of you must be familiar with what's a domain, a codomain, and range and all of those stuff. So this is, let's say, your domain. And if I say that I have two members here, two elements here, x1 and x2, and they're mapping to the same element. That means this is what fx1 and fx2 mean, right? This same point is fx1 and same point is fx2. If this happens, then we say that the function is not one. That means if two elements are mapping if two elements are mapping to the same element, then that's a problem. Then is when we say that it's not one function. So the definition says, what should be the definition then? It should be that if ever the image of two elements is same, then those two elements should also be same, right? That means if the image is coming out to be
Ma'am,
same,
your
then
voice
these
is
two elements should
breaking.
have been same. Then I could say that it's a one-one
Not
function.
clear
So
also.
whenever the image of two functions
Ma'am, your voice is
is it
breaking.
breaking again?
Yes,
Yes,
ma'am.
ma'am.
Not too much.
But in
Is
between
it
some words
the
are
case for everyone or okay? It's the internet issue maybe then. There's not much the domain. This is the definition for your one-one function. So in simple terms, what we're saying here is that if you have two different elements here, then their images should be different here. This should be mapped to some different element, and this should be mapped to some different element. Now, if there are two elements that are mapped to the same element, this should mean that both of these elements are same. They are not different elements. Then we say that it's a one. If so, in simple words, if ever you see that two elements are being mapped to the same element, it's not one-one. Otherwise, it's one-one. That's also what this definition tells us about one-one functions. And then coming on how to identify one-one function, how to tell if a function is one-one or not. So first is ways to check one-oneness, or this is also called injectivity, by the way, injective functions. So first one is your graphical method, the horizontal line test. So horizontal line test says that you just take the graph of that function. And so far, all the kinds of function that we have seen how to plot them, right? We have seen how to plot a polynomial. We've seen how to plot or sketch quadratic functions, then linear functions, all of those we've seen, right? And some of the popular ones we already know how they look like the sine function, the cos function, then the tan function. All of these we already know how they look like. If you don't know, they look like this. They're oscillating. Some of the cos one looks like this. So they're definitely not one-one functions, right? And then you will see one or two types of functions more. And you will be able to identify by their graph only they're one-one or not. So what's the test for a graph? It's like this. If your graph is, let's say this, then horizontal line test says that if you draw any horizontal line parallel to, by horizontal line, we mean a line parallel to your x-axis. So if I draw any line parallel to x-axis, that line should only cross this graph. This is the graph, let's say this is the graph of fx. This should only cut the graph at one point, then I'll say that it's a one-one function. So for example, in this case, if I'll draw this line, this is a horizontal line because it's parallel to x-axis, but it cuts your graph fx at 1, 2, and 3 places. That means that it's not a one-one function, not one-one. Now let's come to this one. What about this one? And to make things simpler, let's take this.
This is a one-to-one.
And this too. This is a straight line. So this is also, this is, let's first come to this one. This is 1, 1, because if you draw any horizontal line here, parallel to x-axis, this line, this line, this line, any horizontal line will only cut this graph. If this is your fx, then these lines, this line only cuts here, this one only cuts here, this one only cuts here. That's why each of these horizontal lines cut this fx graph at only one place. That's why it's a 1, 1 graph. It's 1, 1. Same goes for this one. Any horizontal line is only going to cut this graph once. This is 1, 1 as well. Now, if you will have this, a quadratic one, all these lines, this one is enough for you to see that it's not a 1, 1 function. It cuts your graph at two places, right? Here and here. That's why this is not 1, 1. And if you look at the cubic one, it's like this. This is also 1, 1, because it only cuts your graph one place. One here, and one here. That's your graphical test, the horizontal line test that you can use to check whether your function is 1, 1 or not.
Excuse me, ma'am.
Then the second one is using your definition. Use the definition.
Ma'am, your voice is breaking.
Ma'am left to open.
So just give me a second. I'll share my screen again. There's some internet issue on my end, so I keep getting disconnected. Just 1 second. Okay, so yeah, someone was saying something. Did someone had a doubt somewhere?
Yes, ma'am.
Because
I have a doubt.
yeah, yeah,
Ma'am,
go on.
if a
Yeah,
function
yes,
f is x to y is called one-to-one function if f x1 equal to f x2 belongs to y, then x equal to 1. Sorry, x1 equal to x2.
yeah.
So, ma'am, if x1 equals to x2, so the point are same. So the function will be same. Is it a one? Is it a one?
What? I couldn't hear your question, the last part of it.
Oh, okay. So can I repeat again?
Yeah,
So a function f x to y.
yeah.
Here x is
X.
domain, y is codomain.
Okay, that's not how you say it, but okay. Then,
Is called one to one if f of x1 equal to f of x2 belongs to
yeah,
y, then x1 equal to x2.
belongs to Y. What are you trying? I
Yeah.
don't get it. What's your question?
So is this? I am confused about this statement.
This is the definition. What's your question?
So is it a correct statement?
You're confused about this. Is this a statement in some book?
No, I mean a question.
Uh, Ma'am, sorry to interrupt, but
Can
just want to
you
confirm if this is getting recorded or not.
just do one thing? Just drop the screenshot screenshot of this
Again, your voice is not
statement.
audible.
I'm sorry to
Your
interrupt,
voice
but your
is
voice is breaking.
Yeah, just drop the screenshot of that question if you have it somewhere. Yeah, yeah, this is getting recorded. Okay, so I mean, this is going to happen because as I said, that I have some internet connectivity issue here. So is it better now? So
Yes, ma'am. Clear.
am I still not clearly audible?
Now
now
it's
it's
okay.
audible.
Am I audible?
Yeah, ma'am. Yeah.
Am I audible?
Yes, ma'am.
Okay. What I have some internet connectivity issues at my end. Okay, and I want you to because Okay, can you guys hear me now?
Yes,
Yes,
ma'am.
ma'am.
Oh, so how do we use a definition to prove that a function is one? Let's say you've been given a function fx equals to this function, and then let's assume this thing to be true. Let's say for two elements x1 and x2, the image of these two elements is same. Let's say if this is true, then I have to prove that these two elements are also same. Then is when we show that it's a one function, right? Okay. So this is what you have to prove. Let's start from here. If this is true, then this would mean that your x1 plus 2 is the same as x2 plus 2, right? And this is going to prove that your x1 is the same as x2, right? So that means we started from here and we proved that x1 is equals to x2, which means this is a one function. So this one, x plus 2, is a one function. Now let's come to one more example where we are going to use the definition. Let's take this one, 1 by x plus 5. Now if I'll take this to be the function, then we'll use the definition again. Fx1 is equals to fx2. And we have to show that x1 is equals to x2. So if I start from here, I should get x1 equals to x2. Let's start from here. If fx1 is equals to fx2, that means 1 by x1 plus 5 is the same as 1 by x2 plus 5. What does this mean? This means that x1 plus 5 is the same as x2 plus 5, right? And what does this mean? This means x1 is the same as x2. So we have reached our conclusion that x1 is equals to x2. That means this function is 1, 1. Now let's come to one more function, which is, let's take x square this time, or x square plus 1. If this is your function, then you will have x1 square plus 1 is equals to x2 square plus 1. Let's start from here. So you will get x1 square is equals to x2 square. Now from here, can I conclude that x1 and x2 should be equal? So if the squares of two, this means if the square of two elements or two numbers is same, then the numbers should be same, which isn't true, right? Or if you really want to solve it,
It can also be negative.
Yeah, it can be negative, or if you just want to do it arithmetically, you can do this. X1 square minus x2 square is equals to 0, which will give you x1 plus x2, x1 minus x2 equals to 0. Now, if this is 0, then one of this should happen, right? Either this factor is 0, x1 is equals to x2 because they're both linear, or x1 is equals to minus x2, right? Either this one is 0 or this one is 0. Is this okay? That means you have two ways to get this 0. So either you can take x1 to be equal to x2, or x1 square and x2 square are going to be equal even if x1, x2 are not equal, but x1 is the negative of x2, right? So that means not 1, 1. Now if I'll do the same for x cube plus 1, or x cube, let's say if I'll do this for x cube plus 1, then what's going to happen? So we'll have x1 cube plus 1 is equals to x2 cube plus 1. And this will be x1 cube is equals to x2 cube. Now, if you have two numbers, the same concept does not apply here. The negative of, if you will take the cube of a negative number, you will get a negative number. If you will take the cube of a positive number, you will get a positive number. So the negative positive thing does not happen here. And further, if you want to check it, there's identity for x1 cube minus x2 cube, right? Which is x1 minus x2. But if you don't want to use, that's why I say that for this one, if you want to use it, if you want to use the definition here, that's fine too. But the better approach here is to use the graphical method, right? The horizontal line test. And the graph of this one looks like this. So it is x cube and y minus 1. So it will be here. If this is 0, 1, so your graph for x cube plus 1 looks like this. And you can clearly see from here that it's a 1, 1 function. Is that okay? So you just need to know how to plot the graph, because that's easier in this particular case. Otherwise, you know that even if you know that minus, this one's going to require you to know the formula for x1 cube minus, what's the formula for x1 cube minus x2 cube? It's x1 minus x2 and then
Into x1 square plus x1 x2 plus x.
this, right? This
Yes.
is the formula. So if you will find this, then there are two ways. One is when x1, now if you will equate this to be 0, these two are equal. This implies this, this implies this. This implies you have two things here. One is, this implies either your x1 is equals to x2 or x1 square plus x2 square plus x1 x2 is 0. Now, can this happen? If I'll take x1 is equals to, let's take x1 is equals to 1. And if I'll take x2 is equals to 0, no, this is not going to become 0, right? So you'll have to see if this has a solution or not. And
x1 plus x2 whole square.
no, this is not x1 plus x2 whole square. If you really want to write it as the whole square thing, it should be x1 plus x2 whole square minus of x1, x2. This is this expression. And then you will say that this is 0. So basically what you can do is, I don't know if it has a solution or not. You'll have to check if there are two numbers or not, whether x1, that's two numbers x1 and x2, for which this expression becomes 0. And I think there should be a number like, there shouldn't be a number like that. So what we're doing here is, see, we already know by graphical approach, we already know that's why I said you should use the graphical approach here, because it's the easiest and we know what the graph of x cube looks like. That's why I've asked you to use the graphical approach. But if you really want to use the algebra approach here, then you will need to show that this does not have any solution, right? Do you get the point? Which is true. This is not going to have any solution. You are not going to find any real numbers such that this expression becomes 0 for those real numbers. Two different real numbers. So, or even the same ones. Even if they're same, you're not going to get this expression 0, which is why this is 1, 1. What's happening here is, by the definition approach, if there were a solution for this, if you could find x1 and x2 such that this expression becomes 0, then what would happen? If this expression is 0, that means you have a relation, there are x1 and x2 such that both of them not equal. That means this relation is not necessary. Even if this relation is, for this to be 0, you would want this relation to be 0, right? This entire thing to be 0. It's also 0 when this thing is 0. Only this one forces x1 and x2 to be equal. That's why you want this to have no solution. So for those who have understood this, it's good. For those who haven't, you don't have to use this approach. Is that okay? Don't use the definition approach for this one. Use the graphical approach. Okay. Does anyone have a doubt so far? Can we move to the next method?
Yes, ma'am.
Okay. So the next method is, let's say you have to see if it's 1, 1 or not, right? So what you can do is, if you can see, do this thing. Let's say your function is y is equals to fx. Then if y is equals to fx has only one, not this thing. If fx is equals to c has only one root, what does it mean? If for all c belonging to real numbers, that means no matter what real number I take, if fx is equals to c has one root, what does it mean?
It may be a linear function.
Has at most one, let me just say, has at most one root. In terms of 1, 1 and not 1, 1. If I say that, okay, if I have a function fx and I'm saying for fx equals to 1, I only have one root. That means there's only one x1, which gives you value 1. There's only one x2, which gives you value 1.5. There's only one x, which gives you value 1.7. What does it mean? So either there's just one x, which gives you a certain value, or there is no x, which gives you that value. What does it mean? It means no two x's can take the same value, right? If there were two x's, x1 and x2, such that fx1 different. When do we have a function not 1, 1? Not 1, 1 is when for two different x, fx1 is equals to fx2, right?
Yes, sir.
That's when we say that two functions are not one. This function is not 1, 1 because for two different values of x, you're getting same value of f. So if I'll say that fx is equals to c has only one root, or it can at most have one root, that means either there is an x such that fx is equals to c, or there is no x for some c. Let's say for 1, there is no x. For 2, there is 1x. For 2.66, there is 1x. Then what does it mean? That means for all c, if you will take any c, no matter what, this equation is going to have either one solution or no solution. That means no two x's can take the same value, because if they took same values, then this would mean, let's say they're taking value r. That would mean that fx is equals to r as two solutions, right? x1 and x2, and they are different. Is that fine? So one way to check is that you have to make sure that fx is equals to c has at most one root. It only has one root or no root at all. That's also fine. Is this point clear to all?
Yes, sir.
Okay. So let's do one example on this one. Let's say we have x cube plus 5x square plus 6x plus 16. Let's say this is your function and you have to check whether this is 1, 1 or not. One way is you can try plotting the graph of it if you can.
No, it
And if
is
you see,
not 1, 2.
if it's something like this, which is what I suspect that it's going to be something like, it's going to have some turning points. And the moment your function has you can also check it using the turning points, by the way. We have another method. If you see that your function has a turning point, that means it's not 1, 1, right? If your function has a turning point, it cannot be 1, 1 then. But that's not what I was going to use here. Let's say I equate this to 0. Let's say I'll equate this to 0. You can equate it to anything and then check if it can have two solutions or not. But I am equating it to 0. Then let's see this thing. X cube plus 5x square plus 6x. Let's check for this one if this can be 0 or not for two different x. If this function can be 0, this one. If this is 0 for two different x, that means if x1 cube plus 5x1 square plus 6x1 is 0, and x2 cube plus 5x2 cube plus 6x2 is also 0, then this will also be 0 for two different values of x, right? The constant does not change anything. If the non-constant part, this one, is 0 or takes some value, let's say if this part is 0 for x1 and x2, for two values of x, this part is 0. That means this entire part, including 16, is 16 for both x1 and x2, right? Is this clear? There are two things that I need to make sure. One is that I'm audible because I keep getting this corrected. And second is if it's understood or not. So
Yes,
please
ma'am,
keep
you are audible.
responding.
Yes, you
Okay.
are audible.
So what we've discussed, do you want me to repeat this part?
I actually joined in pretty late, so I will like go for the recording. That's why I asked for the recording if it's there or not.
Okay.
So, uh,
Okay. So for other people, is this understood? The thing that we're doing here is we're saying this function is 1, 1 or it's not 1, 1. How do you check it's not 1, 1? That if for different x1 and x2, if there are two different x1 and x2, such that this function takes the same value for these two. So how do you check? Let's check it for 0. Let's say, can two different x give you 0 for the same function? So what we're doing things, let's forget about that first. Let's say this thing. If you have f of x and f of x is 1, 1, then can I say that f of x plus some constant is also 1, 1? Can we do that?
Yes.
Right?
Yes,
So,
ma'am.
and this goes both ways. If fx is 1, 1, then fx and added with some constant, that also should be 1, 1. So same we're doing here. So instead of checking whether this is 1, 1 or not, one thing that we can do is check whether this is 1, 1 or not. Just this part. Remove the constant part. We don't need that. Because if this part is 1, 1, non-constant one, then the constant added to it will also be 1, 1 because of this.
Okay.
So
Okay, ma'am.
we'll only check for this one. Now what we're doing here is forget about everything else. Just take x common from here. Do you see that x is common here?
Yes, ma'am.
It's x and then you will have x squared plus 5x plus 6 is equals to 0. That means x is equals to 0 gives you 0 and x is equals to roots of this. What are the roots of this? It's 2 minus 2, right? Minus 2 should be a root. And
2 and -3.
is it, how's 2 a root? This is all positive, right?
Both are minus.
If you will split it as 2x and 3x, you'll have x,
2 and
x
3.
plus. Okay, so 2 and
Both
3 are the roots. Let's not bother about that. You're going to have two roots. X is equals to 2 and 3, whatever it is. Whatever the signs are, we're not bothered about the signs, but you're going to have two roots from here, right? That means for x is equals to 0, x is equals to 2, and x is equals to 3, you're going to get the same value 0. That means 0 value is attained at 3 points. F of 0 is also 0. F of 2 is also 0. F of 3 is also 0. Or I shouldn't call this f, I should call this gx instead, because f is this, right? So that means your g of 0 is 0, g of 2 is also 0, and g of 3 is also 0. That means f of 0 is 16, f of 2 is also 16, and f of 3 is also 16, right?
Yeah.
That means at 3 different points, you're getting the same value. That's one way you can check. And we have particularly chosen 0 here. Sometimes what happens is, let's say if instead you have gotten something else here, you can choose some other constant too, that's fine. If you can find the root for this is equals to c easier than 0, then just put this equals to c and try to find if you can have more than one root for this equation. If you can have more than one root for this equation, that means it's not 1, 1. I've taken this here. Is this fine so far?
Yes, ma'am.
Okay. Then we have another method to do it, which is increasing, decreasing, and it's a theorem. So any strictly increasing function or strictly decreasing function, strictly increasing or strictly decreasing, is 1, 1. So you don't have to check for such functions. If you have a function which is strictly increasing or it's strictly decreasing, not both. By this, I don't mean that in this interval it's strictly increasing, then in some other interval it's strictly decreasing. I mean on the entire domain, if it's strictly increasing and strictly decreasing, then we say that it's a 1, 1 function. It's like this only, that if you have something like this, it's strictly increasing, then the horizontal, you can see why it's 1, 1, right? Because the horizontal line test would pass here. This would pass the horizontal line test, that's why. So for a strictly increasing or strictly decreasing function, it's a 1, 1 function. And we've already discussed what strictly increasing and decreasing functions are, right? In previous lectures. Should I discuss that again?
We have
Is everyone
discussed it.
familiar with these two terms? Strictly increasing is different from increasing. We don't mean increasing here. Okay. So that's one way to check. And how do you check strictly increasing? One way to do is that if your f dash x is strictly greater than 0, I know you've not done derivatives, but whenever you will do derivatives, you can use that knowledge here as well. That if your function's derivative is always greater than 0, that means your function is strictly increasing, which should mean that it's a 1, 1 function.
It means the slope is positive. Okay.
Okay. So then we have the exponential functions. So exponential functions are of this kind, where you have fx is equals to a to the power x. This is called exponential function. Or for particular, let's take, this is the general form. This is general form for exponential function. If you want a for quadratic ones, you do this, right? Ax square plus bx plus c. This is the general form for quadratic functions. Similarly, this is the general form for exponential functions, where your x varies and a is a constant. A belongs to R, is a constant. The example, let's take a particular example, like let's take fx is equals to 2 to the power x. So this is an exponential function. And then we'll discuss the properties of exponential functions. So basically in your exponential functions, first is a to the power s and a to the power t. If this is it, then you can add the powers. This will become a to the power s plus t. This is basically a operated s number of times. But when you write a to the power x or 2 to the power x, and let's say I have 2 to the power 1.5, then you can't say that 2 is operated 1.5 number of times or 1.7 number of times, right? So, but that's the core idea here. So your powers get added here. The second one is a to the power s divided by a to the power t. So similarly, when you multiply them, the powers get added. When you divide them, the powers get subtracted here. A to the power s minus t. The third one is a to the power 0 is equals to 1. That's a property. So any number raised to the power 0 is 1. Fourth one is 1 by as. This, I should have written this one next. So 1 by a to the power s is a to the power minus s. So when you have a negative power, that means it's 1 by a to the power s. And fifth one is a to the power s, and then this entire thing to the power t is the same as a to the power st. And then ab to the power s is the same as a to the power s and b to the power s. We forgot one more here. I should have written. Okay, I'll write that here. Seventh one. It is similar to this one, which is a to the power s or a to the power m by n. If I'll take a to the power m by n, this means a to the power m, and this whole to the power 1 by n. And power 1 by n basically means, maybe I should write power 1 by n first. A to the power 1 by n basically means the nth root of a. So what does nth root of a mean? It means a when, let's say I'm saying a to the power 1 by n, nth root of a is b. This should mean that b to the power n is a. So a number which when raised to power n gives you a is the nth root of a. Is this okay? Like when you do power half, this basically like 4 to the power half. It means you're trying to find the number which when multiplied 2 times gives you 4. Similarly, when you are doing 4 to the power 1 by 3, it means you're trying to find the number a, which when multiplied 3 number of times gives you 4, right? So similarly here, a to the power 1 by n means a number which when multiplied n number of times gives you a, and this is written in this manner or this manner. Both of them are same. Just notations. And then 8 is a to the power, if you have a to the power m by n, this means a to the power m, and this entire thing in the nth root. That means a is raised to the power m, and then you've taken the nth root of it. Is this okay? These are the basic properties of your exponential function, a to the power x. How do you add how do you multiply exponents and all? That's it.
Ma'am, can you hold on over it for us for a minute? I need to read
Yeah.
it out.
Ma'am, good evening. Just now I was able to join. Can you hear me?
Yeah.
Okay. Because we were actually told, I don't know which session it was, just before the revision, we were told the deadline will be postponed, not on
Yeah.
Wednesday, but later.
I forgot to ask them to change the deadline, so I'll ask them today.
Okay.
Today is not the deadline, right?
Tomorrow.
Is it?
It's
Okay.
tomorrow.
I'll ask them to change it.
And the second part is like, I think it's not you, but in one of the instructor session, I requested, because still there is an ambiguity, because in the calendar it just says instructor session and we are not clear.
Yeah, okay. We'll change that. We'll name the sessions there.
Okay. And when can we expect the deadline, the postponed deadline?
Tomorrow.
Oh, I mean to say that when it will be, I mean, how many days?
Okay. You mean how? Okay. So today is what?
It's Tuesday.
It's Tuesday, right? So Friday is fine, right?
Yeah. I mean, because today only we are having a summary, so we will get, if we get a couple of days, it will be good to that we can actually, again, because just now I was able to join your session also.
Okay. So let's have it on Saturday. Is Saturday fine for everyone?
Yes, ma'am.
Yeah,
Okay.
Yes, ma'am.
that will be good.
Okay.
Thank
So
you,
is
ma'am.
this one fine? Yeah,
Yeah,
no
I read
problem.
it already. Thank you.
Okay.
Thank you.
So
Thank
these
you.
are the basic properties that you need to know. Do we need to do the examples on these properties too? These are just properties, and I am sure you must have done it in your schools as well, right?
Earlier session during the like TA session, we did it already.
Okay. So then let's come to the proper function, where we'll talk about a to the power x. So a to the power x as a function is, let's say if you have a to the power x, right? And we say that a is a constant number. That means your function could be 1.5 to the power x, 7 to the power x, or minus 2.3 to the power x. This could be your function. Or let's not take negative values, but because we're not taking, this is called the base. A is called the base, x is called the exponent. So we're not taking the bases to be negative. You can take this to be 0.6. You can take all of these things, right? This is a different function, this is a different function, this is a different function. So we need to see how these functions behave. And it depends on a. So how a to the power x is going to behave depends on a. Let's see how it depends on that. Let's say if a is between 0 and 1. Let's take this one. If a is greater than 1 here, and a is between 0 and 1 here. So for example, here you can take a to the power 1.5, or sorry, 1.5 to the power x. So you can take 1.5 to the power x because 1.5 is greater than 1. And then here you can take 0.5 to the power x. This is just these are just very particular examples here and here. You can have a lot of other examples too, right? So first is, let's talk about the domain of this. What's the domain when your a is less than? What's the domain of this one? When a is greater than 1, your entire a to the power x function behaves the same way. That means your function 1.5 to the power x behaves the same way as, it's not exactly the same, but it behaves the same way. 1.7 to the power x, 10 to the power x. They all behave the same way because they are in this category, right? Do we have a doubt? Does anyone have a doubt? And these ones, 0.5 to the power x, 0.6 to the power x, 0.927 to the power x, all of these behave the same way. Same way as in they're not the same functions, but they behave typically the same way. Their basic things are same, like their domain and all of these things are same. So let's see. What's the domain of a to the power x? So a to the power x function is, by the way, this. If you have, why do they behave differently for a less than 1 and for a greater than 1? Let's say you have 2 here. This is when a is greater than 1. Just 1 second. Just give me a minute. Yeah. So this is when your a is greater than 1. Let's take 2. So if I'll have 2, how does 2 to the power x? Let's see some values of 2 to the power x. 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on, right? 2 to the power 1 is 2, then 4, then 8, then 16, then 32, and it keeps increasing, right? That's the pattern that you need to observe, that this keeps increasing. Now let's have, for a less than 1, let's take 0.2 instead, 0.2 to the power x, right? Now your base is less than 1, or you can say now your base is less than 1 and greater than 0. So here you'll have 0.2 to the power 1, then 0.2 to the power 2, then 0.2 to the power 3, and so on. And which is 0.2, then 0.04, then 0.008, and then 0.0016. So these are the values, right? That means this one keeps decreasing. So as you increase
Hello,
the
ma'am. I
power,
have a doubt. Ma'am,
yeah,
I have doubt.
yes,
मैम आप जब पावर बढ़ा रही हैं 2 की, तो क्या वो 0.2 बढ़ रहा है क्या? 0.2 जैसे जो आप लिखी हैं नीचे 2 के नीचे 0.2।
these are two different
नहीं
cases.
नहीं नहीं नहीं, मैं ये कहना चाह रहा हूँ जैसे कि अच्छा ये दोनों डिफरेंट कैसे है? जैसे कि आपने 2
Yeah,
रेस टू पावर 1 लिखा, 2 रेस टू पावर 2 लिखा, एंड 2 रेस टू
yes,
पावर 3 लिखा, ठीक है? एंड नीचे
yeah.
भी तो क्या 2 का आपने 0.2 डेसिमल में कन्वर्ट किया क्या आपने पहले नीचे?
No,
मैं बस
if
इतना
this
पूछ।
confuses you, what
ओके
we are
ओके
studying is, we know that a to the power x behaves differently depending on what the value of a is. If a is greater than 1, then this function behaves differently. If a is between 0 and 1, it behaves differently. So for all a,
ओके मैम।
that's what I said, right? If you have a is equals to 0.5, 0.6, 0.7, 0.927, for all these values of a, all of these behave the same way. more or less the same way. That means
मैम
all
अगर
of
वैल्यू
these are
1 से
decreasing. Yeah, give
मीन
me
द
1
मैम
second.
अगर ओके
Just
ओके
1 second. All of these are decreasing, right? These ones are decreasing. This is one of the properties. Similarly, a lot of properties for when your A is between 0 and 1, the properties remain same. When your A is greater than 1, for those ones, the properties remain the same. That's why we have two columns, right? One for A greater than 1, the other one is for A between these two. So that's what we're seeing here. We're trying to see when we take A greater than 1, we have 2 to the power x as function, right? My A to the power x, the function that I'm discussing, becomes 2 to the power x. Now I can't take all the values. I can't take 2 to the power 0.792. You can't find this, right?
नो मैम वी
So
कांट
what we
फाइंड
do
दिस
is,
बिकॉज़ इट इज
yeah. So that's why what we're doing is we're only taking natural numbers here. So what we're doing is, what we're trying to see is when x increases, what happens to 2 to the power x? So if I'll
मैम
increase
इट
the
आल्सो
power,
इंक्रीज
yeah, that's
टू
also increases for 2 to the
यस
power
मैम
x, but it decreases here, right?
यस
For
मैम
0.2,
when
this
you
decreases.
write whole number then it decreases ना मैम
Yeah. So when you take a number between 0 and 1, this decreases. So what we have found is A to the power x decreases when A is between 1 and 0, right? So if x
यस मैम
increases, A to the power x decreases. And if x increases, A to the power x increases when A is greater than 1, right? I just wanted you guys to notice this thing. That's it. That's why we've done this thing.
ओके मैम मतलब अगर ए से अगर पावर अगर बढ़ाएंगे 1 से तो वो पावर इंक्रीज करेगी हमें यही समझना है केवल ना
Yes.
ओके
So let's come to the domain of this function. Let's say you have A to the power x function or 1.5 to the power x in particular. This is a particular example. In general, it's A to the power x. What's the domain of this? When A is,
मैम
even when A is
डोमेन
greater
भी
than 1. Yeah.
मैम डोमेन विल बी 1.5 आपने जो n लिखा है वो होगा हमारा n
No. Domain is the input values that you can give this function, right? If your
ओके
function is
मैम
1.5 to
10x
the power x, then what all values can x take here?
0 to infinity.
0 to infinity. And what's wrong with the other values, the negative ones?
मैम when you take negative value it will decrease
No. If I can take this, right? 1.5 to the power
sorry
minus
मैम
1. This is 1 by
then you have to
1.5.
reciprocal of
Yeah.
then you to do reciprocal that's why
We just need
you
to
can't take
know that if you, why can't we take this? If you have fx is equals to a to the power x, or let's take, because a is a little, a to the power x is confusing. Let's take 1.5 to the power x. I just need to know what all values can you have for x. Like if you have x here, then I can't take x negative, right? Because it's not valid. Minus 2 in square root is not valid,
no ma'am
right?
root of minus
That's why,
is not by yes
right. That's why minus 2 is not in the domain of square root of x. So that's the question here. What all values can x take?
All
ma'am can I
real.
take minus
All
2
real. All
ma'am
real.
may I take
All real values.
minus 2 value of x
Yeah, you can take, this is what minus 1.5 to the power minus 2 is 1 by 1.5 squared,
0.5
which is 1 by 2.25, I guess. You can find the value, right? It's a real number. This is a real number. What's the problem?
okay ma'am means all real number can be taken as a power
Yeah, you can.
in domain
Yes, you can take all the powers. Any real number can be power. That's why the domain is real numbers. So a domain is real here, and it's real here as well. Even if you'll take 0.5, I can take any power here, right? That's
yes
not
ma'am
an issue. So your domain is R here as well. Then the next one is the graph. Let's look at the graph of this. We already know, or before that, we can just write that this is an increasing function, right?
I'm
Increasing,
sorry
and this
disturb in
one
between
is decreasing. Yes.
ma'am if you take the power ma'am you are taking 1 okay sorry taking 2 and you are taking the power of x by means 1.5 then how can we calculate this
You can't calculate it, doesn't mean it doesn't exist, right? You're saying if I'll take 0.5 to the power, let's say 1.3, this is a valid power, but you can't find the value. You'll have to use a calculator for that, but it's valid. Is that okay?
और कैलकुलेटर ऑन ये
Sorry, what?
means ma'am by calculator we can only find
Yeah.
this value.
You can find that value. That means
Okay,
you
thank
just
you.
need to know that that value exists and that value is real. So if I'll take 1.5 to the power 1.327, I want this value to be real and it's a real number. You'll get a real number when you'll find this.
Okay, ma'am,
Okay.
thank you.
Okay. So this is, we already saw that for a greater than 1, your function is increasing, and for a less than 1, your function is decreasing, right? We just checked it here for this one. So that's one thing. And then let's come to the graph. Or even before coming to the graph, let's first find the range. What's the range of this? Range of 1.5 to the power x. What's the range?
0 to infinity.
0
Minus
to infinity.
infinity.
And is 0 included?
No.
Yeah, so 0 is not included because 1.5 raised to any power cannot give you 0. No matter what power you take here, you are never going to get 0. That means your range is 0 to infinity. So this goes from 0 to infinity. And it cannot have negative numbers as well. Because if you have, why do we not have negative numbers here? Because your A is also positive. So when a positive number is raised to some power, that is always positive. If you have positive here and it's raised to some power x, this is always positive. That's why your range is from 0 to infinity. Same goes here. The range is from 0 to infinity here as well. Or should I just give you the graph first? I thought, okay, this is the graph. This is what the graph looks like. Graph for a to the power x when when a is greater than 1 looks like this. It's this. And this graph looks like this. When a is less than 1 or when a is between 0 and 1, your graph looks like this. That means it's decreasing here. It's coming close to x-axis here. And it's increasing. On this side, it's going to infinity. And same is with this one. On this side, on the positive side, it's going to plus infinity. And on the negative side, it's going to 0. Now you can see why the range is 0 to infinity, right? Yeah.
I mean, first graph then means if it is going in negative, so it is going to 0.
Yeah, this one's on the negative side, it's going to 0. Yeah.
And on positive?
So when on positive, it's, you tell me. We've discussed this in polynomials, right?
Yes, ma'am.
On the positive side, it's going to plus infinity.
Okay, ma'am.
Okay. So then we have this thing. And this point is, this is your, what is this point called?
Y-intercept.
Y-intercept, right? So the y-intercept, and how do you find the y-intercept for a function? Let's say your function, the function was 1.5 to the power x, right? Or a to the power x for a less than, a greater than 1. So if this is your function, what's your y-intercept?
1.5.
1.5.
1.
For y-intercept, you put x equals to 0 and find the value of y. So it's y is equals to 1.5 to the power x. Put x equals to 0 in this equation. You will get y is equals to 1.5 to the power 0. And any number raised to the power 0 is 1. That means your y should be 1. Put x equals to 0. So your y-intercept is 1. And the coordinate will be 0, 1, right? That means this coordinate is 0, 1. Now let's do the same here. If I'll do this for y is equals to
And that
What
means
did we
for
take
every
on the other
function, it
side?
will be one.
What?
For every value of a, it will be 1, right?
Yeah, it will be 1. So if you'll do it here, if you'll put x equals to 0, this is still y is equals to 1. So the y-intercept here is 1 again. This is the y-intercept, and here this is the y-intercept. So y-intercepts for both of these are same. That means this point is also 0, 1. This point is also 0, 1. Y-intercepts are same. Then we have x-intercept, although you don't need to solve the equation for this one. Can you just look at the graph and tell me what's the x-intercept?
No x-intercept.
No
Minus infinity.
x-intercept, right? Minus infinity is not a number. Minus infinity is a limit, so it cannot be x-intercept. Do you see this graph cutting x-axis anywhere? If you will move to minus infinity, it will keep coming closer to this x-axis. It keeps coming closer to x-axis, but it never touches the x-axis. That means you don't have an x-intercept here. And same goes for this one. So this one is, it goes like this. Keeps coming closer to the x-axis, but it never touches the x-axis. So this is it. Here also your x-intercept is no x-intercept. And same goes here. I'm not writing it again. Then let's come to n-term behavior. So for your n-term behavior, when x tends to infinity, where does your y go? Here, look at the graph. When x tends to infinity, this is x tending to infinity or x-axis. Your y is also going to infinity, right? So you can say when x goes to infinity, a to the power x goes to infinity. When x goes to minus infinity, a to the power x goes to here. When x is going to minus infinity, your a to the power x, the function is moving closer to 0, right? Because your height is decreasing each time. Your function is moving closer to the 0. X equals to 0 line. Y equals to 0 line, sorry. Is that okay? So that means when your x tends to minus infinity, your ax tends to 0. And what happens here? When x tends to infinity, where does your a to the power x go this time? It's going to 0, right? And when x tends to minus infinity, a to the power x is going to infinity. So this is it. We've discussed what a to the power x and all the properties of a to the power x are for when a is greater than 1 and for when a is less than 1 and greater than 0. Here. Okay. Then coming to the next topic, it's and e to the power x is 2.7 and something. I don't know the values later. It's an irrational number though, but it's something like this. Then what should be e to the power x? What category should e to the power x fall under? This one or this one?
Increasing.
The increasing one, the first one, right?
Yes.
So this is going to be, this is called natural exponential function. And if you'll, yeah, that's all you need to know about this one. One other thing is that the area under this curve is the curve obviously looks like this. Increasing function, this is the point 0, 1. And the area under this curve, this one, is E. That's it. And you'll know why the area is E when you'll do integrals later. Then you'll see why the area is E. Okay. I'm coming to the next part. Okay, then coming to now let's come to compositions. Do we have onto functions too in our syllabus in this week? The composition of functions is basically FOG. This is composition of functions f, x, and gx, let's say. So how do you compose two functions? Composition is basically this. F of g, these kind of functions are called composition functions, where first you apply g on x. So what's happening here is you have a value x. This is, let's say, domain, some domain. Then you are applying g to this, and you're getting g of d, right? G applied to this set D, and then you're applying F to this thing. That means F of G of D. So for example, let's say you have X. This is how it works. So what you're doing is, it's basically this. You have X, then you apply G to it, and you will get GX, right? And then you apply F to this entire thing. So you will get FG of X. For example, let's say you have a number 1, and then you apply the function G x is equals to x plus 2. And let's say your f is fx is equals to x squared. So if I'll apply on this one, if I'll apply g first, what will I get?
3.
I'll get 3. And then if I'll apply f to g of 1, then what will I get? I'll get f of 3, right? Because g of 1 is 3 and f of 3 is 9. So this is what it means. That first, to this x, first you apply g, and then to this gx, you apply f. Okay. So now let's see some composition functions first. Let's do this one. And let's talk about the domain of composition functions first. Domain of, and this is also written as, this you can write as FOG. In short, we write this as FOG of x. So your FOG of x is nothing but g applied to x first, and then f is applied to gx. That's what FOG of x means. And GOF of x means f applied to x first, and then this to this entire fx, you apply g. So what is the domain of, let's say, FOG? How do you find the domain of this function? Then let's say you have a function FOG of x, which is the same as gx. So first you're applying g to x, and then f to this entire thing. So what should be your domain? What's the domain of FOG? So for you to find the domain of FOG, you have two things. One is that x should be in the domain of g, because you will apply g to x, right? If x is not in the domain of g, then can I apply g to it?
No.
Right? So you need x to be, first condition is for x to be in domain of FOG. First condition is that x should be in the domain of g, because you're going to apply g first and then you will apply f. And what's the second condition? That your gx should be in the domain of f, right? Is this okay? So x should be in domain of g and gx should be in domain of f. These two conditions need to be, so if there is any x in the domain of FOG, then that x should be in the domain of g, because you're going to apply g to it. Like, and then that gx, the value that you will get, that should be in the domain of f. Let's do one example first. Let's say you have x squared, you have root x and x plus 1. Let's say you have these two functions. This is your f, this is your g. Or let's take this as f and this as g. What's your FOG then? Your FOG is
Root of x plus 1.
If you do it one by one, you will get this. FOG of x means gx and then f applied to it. So if you will apply g to x, you will get x plus 1. of f, right? This. And then if you will apply f to x plus 1, you will get square root of x plus 1. So that means now for this to happen, what we've done here is, first thing is, for you to be able to apply g to x, your x should be in the domain of g, right? And then x plus 1. Now let's take 1. For example, let's take x is equals to 1. Is x is equals to 1 in the domain of g? This belongs to domain of g, right? It belongs to domain of g. And then x plus 1 at x is equals to 1 is what? 2, right? And is 2 in the domain of f? You have to check that x should be in domain of g. If you want to check for x is equals to 1, 1 should be in domain of g. And then g of 1 should be in domain of f. So if you're taking this particular example here, for 1 to be in domain of FOG, you would want 1 to be in domain of G and G of 1 to be in domain of F, right? So your 1 is in domain of G, right? You can put 1 here and that's fine. Your input can be 1 for Gx, right? So this is satisfied. And G of 1 is 2, should be in domain of F. Is 2 in domain of F? It's fine, right? That means 2 should be, this condition is also satisfied by 1. This implies, now I can say, because these two conditions are satisfied simultaneously, that means 1 is in domain of FOG. Now let's come to some other number. Let's say I'm taking -2 here. If I'll take x is equals to -2, what will I get?
Possible.
X is equals to -2. I need to check two things. First is -2 should be in the domain of G. And second is G of -2 should be in the domain of F. So your -2 is in the domain of G, right? G is x plus 1, -2 is in the domain of G. So this is satisfied. Now let's come to this one. -2, G of -2 is -2 plus 1, which is -1. That is -1 should be in the domain of F. Is -1 in the domain of F?
No.
It's not there. That's why -2. What does this mean? This is incorrect. So one condition has failed. That means -2 is not in the domain of FOG. This is one element which is not in the domain of FOG. And we have seen one element which is in the domain of FOG. Now let's try to find the entire domain. So your domain should be, you have two conditions here, right? First is this one, second is this one. What does it mean then? Domain of FOG, that means should be equal to domain of G. So I want both of these to be met, to be simultaneously true. So we have to take domain of G and then we have to take the collection of X belonging to real numbers such that Gx is in domain of F, right? That means the inner function when applied to X should be in the domain of outer function. And I should take the intersection of both these sets, right? This would mean, now if X is in this domain, that's the definition. If X is here in the domain of FOG, it should be in the domain of G, and intersection means and. So it should be, your X should be in this set and your X should be in this set as well, right? So that's your domain of FOG. Now, how do you find this? Let's take our recent example only. Let's find the domain of this. F of X was root X and G of X was X plus 1. What's the domain of G?
All real numbers.
All real numbers. And then let's come to this set, X belonging to real numbers, such that Gx is in the domain of F. Let's first find domain of F, then only we'll know for what X is Gx in the domain of F, right? What's domain of F?
0 to infinity.
0 to infinity, and 0 is also included. So that means this is the same as x belonging to real numbers such that, and what is g of x? G of x is x plus 1, right? Should be in the set 0 to infinity. This means x such that x plus 1 is greater than equals to 0, right? That's it. I've written this in equation form, inequality form. That's it. This means x such that x is greater than equals to -1. Is this fine? So this
Yes,
set
ma'am.
is equal to this set. This is the same as this set. This set is the same as, they're all the same sets. We've simplified the forms. That's it. So what should this give me? How can I write this thing in intervals? X belonging to real numbers such that x is greater than -1 or equals to -1. So it is x greater than equals to -1 means this thing, right? So this set is the same as this interval. Is this fine so far?
Yes, ma'am.
Okay. So that means I wanted two sets. One is D of G. The domain of f of G is what? Domain of G intersected with x belonging to real numbers such that G of x is in domain of f. Okay, so what is D of G? D of G was real numbers, and this set is 0 to infinity, right? What's the intersection of both these sets? It's like this. 0 to infinity is here. This is 0. Starting from 0, going till infinity. So this is this set, 0 to infinity. And your real line is from here, minus infinity to infinity, right? So the intersection of these two sets is something that's in this set too and something that's in this set too, right? So basically this one. I want it to be in this set too. And I want it to be in this set too. Is this example clear to all? Then
Yes,
we
ma'am.
can move to the next example if this one's clear. Okay, so let's try to do this one. Fx is equals to 1 by x and gx is equals to x square
In
minus
this
4.
statement, in the intersection statement, what about -1?
We had my, okay, sorry. I thought this is what we've found. Thanks for correcting it. We had -1 here, right? This set was equal to, this is this set. It was equal to -1 to infinity. So this is from -1 to infinity. And here you will have -1 then. And this will also change then. You will have -1 to infinity. Is this okay?
Yes.
Okay. So this is the next example. Let's do FOG first. So your FOG is 1 by x square minus 4, right? But we need to check the domain. What's the domain of this? Domain of FOG is, let's first find, for domain of FOG, we first need the domain of G, which is your G is x square minus 4, right? So what's the domain for x square minus 4? This function. It's the entire real line, right? All real numbers. You can put any real number here. No problem. So the domain of G is R. Now let's come to domain of F because we also need that. What's domain of F?
0 to infinity. 0 excluded.
0 to infinity. Why?
All real numbers except 0.
Yeah. So you'll have all real numbers except 0. That means this set minus the 0 set. Okay. So this is your domain of F. And then you have to find this set, X belonging to real numbers, such that G of X is in the domain of F, right? Domain of F, which is equal to R minus 0. This set is the same as X belonging to real numbers. What is G of X? G of X is X square minus 4, such that X square minus 4 does it belongs to this set. When I say that this should belong to R minus 0, what does it mean? It means that this value should not be 0, right? This can take all values other than 0. So I can simplify it and write X square minus 4 should not be 0. Right? When is X square minus 4 0? It's when X square is equals to 4. So this is the same set as,
X equals
what do
to
I
2.
want? I want X square to be not equals to 4. So this would mean, when do I have X square is equals to 4? It's when X is equals to minus 2 and X is equals to plus 2, right? That means I don't have a problem other than at minus 2 and 2, because I don't want the square to be 4. That means I don't want X to be minus 2 or plus 2. Other than that, all values of X are fine. That means I only have a problem at minus 2 and plus 2. That's it. So that means this other set of R's for the intersection is this. Now you have two sets for domain of FOG. Domain of G was real numbers and it's intersected with R minus 2 and 2. So the intersection is going to be R when intersected with any set gives you that set only, provided that set is a subset. This is a subset of R, right? This is a subset of R. So that means you should get R minus 2 and 2. That's the domain for FOG. And if you don't want to go through this entire process, right, you can just have a look at this thing. You can just have a look at the function FOG, and then you can see that for this function, the only thing that's going to create a problem is minus 2 and plus 2. Other than that, we're fine with everything, right? Okay. Let's see one thing here, which is, let's say you have one function, fx is equals to x square, and then the other function is gx is equals to square root of x. Then what is FOG? What is FOG of x?
X.
X. So you will have square root of x and then the square of this, right? And then this will be x. And what about GOF? Here, let me just clarify this. Here we have the domain x belonging to R, and here the domain is x belonging to R positive union 0. R positive means this is positive real numbers and this is 0. What is GOF?
Again X.
Yeah. What's GOF? So GOF will be, let's see how we can write this. G is square root and then x square, right? This is your GOF of x. And what is this value? So this value is mod x. Why is it mod x and not x? This is not equals to x, by the way. This is not x, this is mod x. And why is it so? Because if you have, let's say, if you have minus 1 here, if your x is equals to minus 1, then minus 1 square and then square root of this is 1. And x is equals to 1, you will get 1 square is equals to 1. So this means when I put minus 1, I get 1. And when I put 1, I get 1. Or in simple words, in more generalized words, it's when I put a negative number, I get it positive. I get the solution as positive of it. That means if I'll put -10 here, I'll get 10.
Ma'am,
But if I'll put 10, I'll get 10. Yeah.
I'm sorry, but is this week syllabus is completed?
What?
Is this week syllabus completed until now?
No, the syllabus is not completed. We're left with inverses.
Okay, ma'am.
Okay. So because of this reason, this turns out to be mod x and not x. So what's the domain of, let's come to the domain of FOG in this one. What's the domain for FOG? So if you'll have FOG, you just need to check the values of x. If you'll quickly check it, the domain of G is R, right? So it will be real numbers and then intersection with x such that G of x, that means square root of x, is in the domain of this. And because the domain is real, the entire real line, so this is going to be the intersection with your only, okay, the domain of G is, we've written this wrong. This is, do we need to do the domain of this one, domain of FOG and all, because we've done a similar example where we did x square and or maybe mod x square root of x and x minus 1. We've done a similar example. Do we need to do this here? Can you find the domain of FOG and GOF for this one, or should we do it here? Okay, let's move to the other example. So we're doing a last example on how to find the domain. Let's say you have to find the domain of the function square root of x minus 1 and x plus 2. So if you have to find the domain of this, how do you find the domain? It's the composition of two functions. If you see, it's the composition of square root of x. And g is x minus 1 and x plus 2. And this entire function that's written here is FOG. So the domain of FOG is so your domain of FOG is the domain of G intersected with X belonging to real numbers such that G of X is in domain of F. What's the domain of G? G is this. You have to find the domain of this, and this is what's the domain? We know the domain of F, right? So let's solve this set first. This will be X belonging to real numbers such that Gx, which is X minus 1, X plus 2, is in the domain of F, and domain of F is
R minus 0.
the connectivity issue at my end. So this session's okay. So this one is your domain of F is greater than domain of F is this, right? 0 to infinity. That means you need X such that X minus 1 and X plus 2 is greater than 0. Okay, so you need this equation to be true, right?
Yes, ma'am.
Okay, so this is this thing is, if you want this, if you want x minus 1, x minus, let's say, x plus 2 to be greater than 0 or greater than equals to 0, then what do you want? Either you want both of these to be positive, right? Or you want both of them to be negative. It's like this. If you multiply two positive numbers, you get a positive numbers, or when you multiply two negatives, you get a positive number. If they are of opposite signs, then you'll get a negative number, right? So for this entire thing to be greater than 0, same goes for this one. If you have, let's say, x plus 1, x plus 2, x plus 3, then what would you want? Either you will want these two to be positive, all three to be positive, or you would want these two to be negative, this to be positive, or you would want, do we have other choices? These two to be negative, this one positive, or these two to be negative and this one positive, right? So you'll have to see signs as per this. But for now, because we only have two factors here, two linear factors, so we'll only go by these two. So your two cases here are, if you want the product of these two to be greater than 0, then there are two cases. Either both of them are greater than 0, x minus 1 and x plus 2, both are greater than 0, or greater than equals to 0. Or you have x minus 2 and x plus 2. Both of them are less than 0, right? So if these both of them are greater than 0, x minus 1 greater than equals to 0 means x greater than equals to 1 and x greater than equals to minus 2, right? This means now if x is greater than 1, 1 is here, minus 2 is here. And they have, because we have an and here, that means both of the conditions need to be satisfied simultaneously. That means it's from 1 to infinity and minus, so your x should be in this interval 1 to infinity and in this interval minus 2 to infinity. It should be both greater than 1 and greater than minus 2. A number greater than 1 and minus 2 both. So I can simply write this as greater than equals to 1, right? Any numbers which is greater than 1 is also greater than minus 2. That means this is it. For both of these to be greater than 0, I want x to be greater than equals to 1. That means x should belong to this interval 1 to infinity, right? And let's come to this one then. This one is, you want both of them to be negative. That means you want x minus 2 to be less than equals to 0 and x, this was 1, right? Yeah. So this was minus 1. So you want x minus 1 to be less than equals to 0 and x plus 2 to be less than equals to 0. Both of them to be less than 0 simultaneously. That means x should be less than equals to 1 and x should be less than equals to minus 2. Now if you have x less than equals to 1 and x less than equals to minus 2, then I can simply write this as x less than equals to minus 2, right? If it's less than minus 2, it's obviously less than equals to 1 as well. So this means interval here is x belonging to minus infinity to minus 2, right? This is the interval here. And now what does this tell us? This tells us that if you want this thing to be greater than 0, you want either this or this, right? Either I want both the factors to be greater than 0 or I want both the factors to be less than 0. So from here I get this interval and from here I get this interval. That means the set that I'm looking for, x belonging to R, such that g of x belongs to domain of f, what should it be equal to? It should be 1 to infinity. And should I use intersection here or union here? I know it has to do with these two sets.
Union.
Right. So you'll have to use union here because it's or here. It means even if x satisfy this condition, then also it's fine. If x satisfy this condition, then also it's fine. It doesn't have to satisfy both conditions. It can satisfy either of these or both of these if it can. Right? It was minus 2 here. So this is this other set. And then let's come to this one. We have to find domain of G as well, right? So domain of G is your g was x minus 1 and x plus 2, right? What's the domain of this? X minus 1, x plus 2. What's the domain of this function?
All real.
All real numbers, we don't have a problem here. For any x, you will have an output, right? So all real numbers. That means your intersection will be R intersected with this set. Where is it? This one. R intersection with 1 to infinity, union minus infinity to minus 2. 2 was included, right? Yeah. That means it's just 1 to infinity, union minus infinity to minus 2. That's it. Is this okay? Okay, then we are only left with inverses of functions. So let's do that too. The inverse of a function is, let's say you have fx, then gx such that FOG of x and GOF of x both is equal to x. That means if I'll apply FOG to x, I should get x. And if I'll apply GOF to x, I should get x again. If this is happening, then I say the G is inverse of GX is inverse of F. And inverse of F is denoted by this. F inverse. That is F inverse. So we can say that F inverse is GX. Because G, when operated with F from both sides, from the right side, from the left side, it gives you identity function. This is FOG is equals to GOF is equals to identity function, right? Okay, then let's see how you can find the inverses. Let's do one example on how to find an inverse. And before that, let's see when inverse exists. So F has inverse. F is a function. It has an inverse function if and only if F is both 1, 1 and onto. 1, 1 and onto. So when it's both 1, 1 and onto, then it has an inverse. And if it has an inverse, it has to be 1, 1 and onto both. Let's do one example on how to find inverse. Let's say a function fx is equals to 2x plus 1 and x minus 4. Then to find a function g of x such that f g of x is equals to x and g f of x is also x. You have to find this function, right? And how do you find this g? Just take fx is equals to y. You will have y is equals to 2x plus 1, x minus 4, and then solve for x from here. By solve for x, I mean write x in terms of y. For now, you have y in terms of x. Y is in terms of x, right? I want x in terms of y. So I can do yx minus 4 is equals to 2x plus 1. This is going to give me yx minus 4y is equals to 2x plus 1. And then you can take x on the same side. You will have yx minus 2x is equals to 4y plus 1. Take x common from here. You will have y minus 2. And this will be 4y plus 1. So that means your x in terms of y is 4y plus 1 and y minus 2. So this is x in terms of y. You have to get this expression. From y in terms of x, you want the expression x in terms of y. And then your gx is simply replace y with an x. So you will get 4x plus 1 and x minus 2. This is the inverse function. Is inverse of fx is equals to 2x plus 1 and x minus 4. Is this okay? That's how you find the inverse. And then there are some things about inverse functions, which is, let's say you have f and then you have inverse function of f inverse of x. So one thing is that they are mirror images of each other when the mirror is placed along the y is equals to x axis, y is equals to x line. So if you have a line here, y is equals to x line looks like this. right? Inclination at 45 degrees with x-axis. This is your y is equals to x line. If this is your curve fx, then the inverse of this is going to be the mirror image of this function when this is the mirror. So if you will consider this to be the mirror, then the mirror image here will be the inverse of this. This will be your inverse function. That's one thing about the graphs of in f and f inverse. And then if AB lies on fx, if I say a point lies on the curve y is equals to fx, what does it mean? This says that if there is a point AB, let's say this point is AB. If there's one point AB which lies on fx, then BA, the opposite of it, let's say 1, 2 lies on fx. That means 2, 1 is going to lie on f inverse of x. And what do we mean when we say that a point lies on f of x or on the curve here? If I say AB is here, what do we mean by this? We mean that AB satisfies this function, right? That means if I put y is equals to b, this is y coordinate, and x is equals to a, then this should be true. That means the image of this function at a should be equal to b. That's when I say that AB is going to lie on this function, right? This is the same as y is a here, and this is f inverse of b. And do you see why these two statements are true? Because if you have b is equals to fa, and then if I'll just apply f inverse of on both sides of this equation, I'll get f inverse of b, and here I'll get f inverse f of a. And we've discussed this, that a function when is composed with itself gives you identity function. F inverse of fa is the same as a, right? So this means f inverse of b is a. So this gives you this. This implies this. That means if AB lies on your curve fx, then BA is going to lie on the curve f inverse of x. Okay. And then one last thing, that if you have intersection of f and f inverse, and f inverse function, how do you find the intersection point of two functions? That means fx should be equal to f inverse of x. This is only true. So if there is a point x which lies on both intersection of f and f inverse, means there's a point which lies on f and it lies on f inverse 2, right? That's what you call the point of intersection of two curves. So that's only going to happen. So if x comma y is point of intersection of f and f inverse, this implies xy is a comma a. That means only these kind of points can be the point of intersection of f and f inverse. That means if you have a function, say fx, and the inverse of this function, then can 1, 2 be the point of intersection of these two functions?
No.
Yeah, because it does not look like this. So if you have to have a point of intersection of these two functions, fx and f inverse of x, it should be of this form, a comma a. That means it can be 1, 1, can be 2, 2. That you'll have to check depending on the function, but it cannot be 1, 2. Now, if I say that the point of intersection of fx and f inverse x is of the form a comma a, that means your y is also a. Y coordinate of the point of intersection is also a. X coordinate of that point of intersection is also a. That means your point of intersection always lies on the line y is equals to x, right?
Yes.
So that's it. That's what you need to know. Point of intersection of f and f inverse lies on the line y is equals to x, this line. So if you have f as this, then the inverse of this looks like this, right? If you have this, inverse is going to look like this. This will be f inverse of x, and the point of intersection. This is point of intersection, and this is another point of intersection here, this one. These two lie on y is equals to x line. This is y is equals to x. So with this, we're done with the summary for week 5. Does anyone have a doubt so far in the summary? Do we have any doubts from the summary?
Excuse me, ma'am.
Yes.
Ma'am, I want to know about something about injective function in this summary.
What do you want to know about
Ma'am, you said
injective function?
you said
Yeah.
that the definition. I know about that definition which you told, but actually professor had told us a different definition also. It says that if x1 is not equal to x2, then your fx1 should not be equal to fx.
It's the same thing, right?
It's equivalently a contrapositive
Yeah.
thing, right?
Yeah.
But our
Exactly.
TA, but our
Yeah.
TA session, the TA said that you cannot, if this definition cannot lead you to anywhere, so it's misleading. You cannot use the other definition.
Which one? Which
When
one cannot?
x1 is not equal to x2, 1.
Okay, this definition you're saying x1 is not equals to x2. This should imply it's the same thing as what we discussed. fx1 should not be equal to fx2, right? This is the definition that you're talking about. This is also correct. Are you saying that this definition will not get you anywhere?
Yes, that's the TA said us.
Yeah,
Today.
because if you have to prove this thing, you will say, how will you prove things? Let's say you have a function 2x plus 5. I already know that this is a 1, 1 function. It's a linear function, so it's 1, 1. But if I use this definition, I'll take x1 not equals to x2. Then I try to find, I'll say if x1 is not equal, you can do that too. If x1 is not equals to x2, then 2x1, then you will have to move in the backward direction. That 2x1 should not be equal to 2x2, right? If these two are not equal, then the 2 multiplied with it, but it's not the correct way. It's actually better for you to say, the easier thing could have been if 2x1 is equal to 2x2, then x2 and x1 should be same, right?
Oh, I know that, but I was just about to confirm that this definition is correct or not.
This
As far as-
definition is correct, but for you to use the definition, I'd suggest you to use this one. If you are
Yes.
using the definition to prove, use this thing, but this definition is correct. These two are equivalent statements. They're the same thing. So if you're saying fx1 equals to fx2 should imply x1 is equals to x2, this is the same as saying if I'm saying if these two are equal, these two should be equal. Now, if these two are not equal, then these two should also not be equal, right? That's the contrapositive part. That's correct. But while you're using the definition to prove things, use this thing.
So
Is that okay?
yes,
Yeah.
just I wanted to know that that the definition is correct, right?
Yeah, both of them are correct.
It is not misleading, but only for the proving part we can use the second one.
Yeah. Use this one because this one's for proving you don't actually use it. Even if you want to use this thing, you will indirectly be using this only. That's why for proving stuff, use this one, but this is equivalent to this one. Both of them are equally correct. They are essentially the same statements, just written in different manner. That's it.
Ma'am, I want
Is that okay?
Yes, ma'am, I want
Yeah.
to ask second out. I want to ask you.
Yeah.
Is there any main difference in strictly increasing function and increasing function?
Yeah, there is a huge difference between a strictly increasing function and an increasing function. Strictly increasing and increasing, right? Strictly increasing means if x1 is less than equals. If you have two different numbers, let's say if I say if x1 is less than x2, then my fx1 should be less than equals to fx2. Now, here you have equals to. This says if x1 is here on the real line and x2 is here, then they can have same values. If they have same values, let's say at x1 this is same value, at x2 we have same value, then also we can say that it's a increasing function, but then it's not a strictly increasing function. So basically this is a constant function, right? Let's say this is fx is equals to 2 function, then this is an increasing function. Why? Because whenever you will take x1 less than x2, your fx1, which is 2, fx1 is also 2, fx2 is also 2. This is going to be less than equals to 2. So the statement holds, right? So this is an increasing function, but the strictly increasing definition says that if x1 is less than x2, your fx1 should be this should not be equal. It prohibits you to have these values equal. That means these two values should not be equal. This value should be strictly less than this one. That's what strictly increasing means. That means now if you have something like this, fx is equals to 2 function. This is not a strictly increasing function because let's say at 1 and at 2, 1 is less than 2, but f of 1 is, can I say this? This isn't true, right? F of 1 is also 2 and this is also 2, and 2 is not strictly less than 2. Strictly less means they should not be equal. This has to be strictly less than this. So that's the difference. So a strictly increasing function looks like this. It keeps increasing. Your increasing function could look like this. And then it becomes constant. And then it goes up and then it again becomes constant. So,
Actually,
yeah.
Actually, Professor told us that those functions which are not strictly increasing, we can classify into non-decreasing functions, which are not strictly increasing. They can be non-decreasing function also.
Okay.
That is similar to like if we see a increasing function, we can say it is a non-decreasing function, right?
If you see an increasing function, see, non-decreasing means you're saying if it's strictly increasing, then you can say because it's not becoming constant here. Decreasing also means strictly increasing means it has to go up only. It cannot get constant anywhere. Or in fact, it can at two different points, it cannot have same value, right? At two different points, you cannot have same value for a strictly increasing function. But for an increasing function, at two different points, you can have the same value. Now coming to not decreasing, what does decreasing mean? Decreasing means that it has to be, you're not decreasing is this the same as strictly, if it's not strictly increasing, that means it can be increasing, right? It can still be increasing. If you have a function and I say it's not strictly, if I say it's strictly increasing, this means it's increasing. If I say there's a function and it's not strictly increasing, then I don't know about decreasing and increasing. Don't know about increasing. Whether it's increasing or not, we don't know. A not strictly increasing function can be increasing or it can't be increasing. We don't know about it. But a strictly increasing function is always increasing. Similarly, if you have an increasing function, I cannot say that it's a strictly increasing function. And about the not decreasing part, if you have a strictly increasing mean it keeps increasing, and non-decreasing means it should not decrease. That's it. What definition are they using? Because different books use different terminology. So what definition have you read?
I think it was the lesson told by Vishal, sir, and he said in I think he said strictly increasing function is different and not decreasing function is different. Because
That's basically the terminology. That's why I said. So in your course lectures, you can check what terminology in. By terminology, I mean different courses use different terminology, right? So you need to check what terminology is used in this course. Is that okay? Okay. Does anyone else has anything? Can we end the session then, if no one has any doubts? Okay, so we'll end the session here then.